So towards the end of the last video on computing a line of best fit, we introduced this idea that such a line, when we put a line of best fit through our data, we're really trying to get as close as possible to some true statistical model, some underlying true statistical model. And we said that this was, okay, any data point from my variable y can be represented by a linear function of the corresponding data point from my variable xi. Okay, but obviously this wasn't going to be a perfect relationship, and so that we represented the fact it was slightly imperfect with this little error term, epsilon. Okay, and we also said that, okay, in the process of finding this line of best fit, what we are doing is we are finding an estimate. We are finding an estimate for this model. Okay, and that estimate was that, okay, well, a particular observation for my variable yi is going to be a linear combination of, so some linear function of the corresponding observation for my variable x plus some corresponding error term. And see, what we've done here is we've replaced beta 0 and beta 1 with b0 and b1. And whilst beta 0 and beta 1 are sort of objects, we don't really know what they are. B0 and B1, well, in reality, when we do a fitting problem, when we compute a line of best fit, these are going to be particular numbers. And so that's what we're going to cover today. We're going to cover computing a formula for B0 and B1. And so remember that we said that this line of best fit in our data, okay, was such that we minimize the sum of the squares of all these error terms, ei. So we minimize the sum from I equals 1 to n of ei squared. Okay. This is a decent starting point, but it's useful if we can express this error term in terms of, our data, x and y, and our guesses for beta 0 and beta 1, b0 and b1. And so we can rearrange this equation here and can take b0 plus b1xi over to the other side and write ei is going to be equal to yi, the data point from the variable y, minus b0 minus b1 times xi. Okay? And so we could rewrite this. We could say that this sum here, we can substitute in this equation for the ith error. Okay? We can write this as the sum from I equals 1 to n of, not ei, but yi minus b0 minus b1 times xi. Okay. All squared, just like in the equation above. And we're not going to go through the nitty-gritty of deriving a minimization of this. We're just going to skip straight to the answer, but it's useful to sort of inspect what's inside this equation here. We have an equation that is simply a function of some data. So yi is data, xi is data. We can't change these. We're not allowed to change these. These are our data. But the two things we are allowed to change are b0 and b1. And so notice there's only two types of things in this equation. Data and our guesses for our population parameters b0 and b1. Okay? And so this makes a lot of sense. And so we can just move b0 and b1 around until this whole expression is minimized. Because we can't move yi around. We can't move xi around like we can move b0 and b1 around. And let's say we solve this problem in the general case. What we're going to get when we solve this problem is a set of formulas. A set of formulas for b1 and b0. Okay? And so let's write these out. Let's look at what these are. Okay, so the formula for b1 when we solve this minimization problem is going to be b1 is going to be equal to the sum over all of our observations from I equals 1 to n of xi minus x bar, which is the sample mean of x, times yi minus y bar, okay, divided by the sum, again, over all our observations from I equals 1 to n of xi minus x bar all squared. Okay? And so, these two expressions on the numerator and denominator of this fraction that represents b1 should look relatively familiar. And this should look familiar from our equation for the sample variance, but also from our equation for the population variance. And the numerator should look familiar from our equation for the sample covariance or even the population covariance. And so since we have just a sample of data here, we don't have the population's worth of data. We're going to think about how these relate to the sample variance and the sample covariance, okay? And we'll notice, well, what we're allowed to do when we've got a fraction like this is we're allowed to multiply this fraction by 1, okay? And we can multiply this fraction by 1 by multiplying the top and the bottom by the same number. And the number that I'm going to multiply the top and the bottom by is 1 on n minus 1. And so I'm going to divide the top by n minus 1, where n is the sample size. I'm going to divide the bottom by n minus 1. Okay? So this original equation, this sum of xi minus x bar, yi minus y bar, divided by the sum of xi minus x bar squared, we can take that to be the definition of b1. But if we times b1 by 1 by dividing the top and the bottom by n minus 1, we get a different expression for b1. And of course, we know that if we take xi minus x bar times yi minus y bar, sum them all up and divide them by the sample size minus 1, well, this is going to give us the sample covariance between the two variables x and y, and we call this S subscript xy. And we know when we sum up the deviations of x from its sample mean, and we square them all, we divide by the sample size n minus 1, well, this is just going to be the variance of our variable x, the sample variance of our variable x. And so if we want to compute this ordinary least squares estimate of this true model, all we have to do is compute the sample covariance and divide it by the sample variance for our independent variable, that is x. Okay. And so this is the harder formula. This is the more difficult formula. Once we figure out what b1 is, it's rather easy to figure out what b0 is. Okay. And so b0 is going to be y bar minus b1 times x bar. Remember, y bar is the sample mean for y, x bar is the sample mean for x. Okay, and so let's sort of assess why this is the case. And we can rewrite this. We can rewrite this as y bar equals b0 plus b1 x bar. And this sort of looks like our equation up here, except we've replaced the ith observation with the average of y, and the ith observation for x with the average of x, and for some reason we don't have an error term. And so it's a property of this model, that it's going to be exactly true at the sample means. That's just sort of a nifty property. And because of that property, if we've got our estimate for the slope of this linear function, we can just plug it into this equation and put in our sample means to get the estimate for the y-intercept of this linear equation. Okay? And so we can see now we've pretty much done with our problem. If we've got a set of data, all we have to do is compute the sample covariance and the sample variance for x, and then we have to compute the two means, and we can get estimates for beta 0 and beta 1 in the form of b0 and b1. So let's suppose that I have some data, I've collected some data, and in that data, the sample mean of x is 10, the sample mean of y turns out to be 20, and I compute the sample covariance of these two variables, okay, S, X, Y, and it turns out to be 0.9. Okay, and I compute the sample variance of my variable x, and it turns out to be 0.3. And so we can compute the estimate for beta 1, which is b1, straight away. We can say, okay, b1, well, our estimate for beta 1 is going to be sxy, which is 0.9, divided by 0.3. And that's going to just be 3. And now, if we want to find out b0, we just have to say, okay, it's going to be equal to y bar, which was 20, minus b1, which we've got now, it's 3, minus 3 times x bar, which was 10. So it's going to be 20 minus 30, which is going to be negative 10. And so we can report our estimating equation. We can say, okay, well, under this model, I've computed my estimates for beta 0 and my estimate for beta 1. And I can say, okay, yi is going to be equal to minus 10 plus 3 times xi plus some error term.